Thank you very much for your introduction, Alexei. I'd like to, can you hear me?
Yes.
Yeah, okay, perfect. So I would like to thank the organizer for this invitation. I'm actually very honored to participate to this session. And also I'm very sad that I'm not able to use this opportunity to come back in Clermont-Ferrand for a while. But anyway, so today I will present you a recent work that we did at Monash University in the group of Jesper Levinson and Mira Parrish on Polariton interactions in microcavity with two-dimensional semiconductor layers. And I have added here a subtitle, enhanced interaction through strong light matter coupling. And I really hope the meaning of this sentence will become clear at the end of my talk. So the outline is the following. After a quick introduction, I will present you our model where we consider exciton as structureless bosons, and we also consider multilayer cavity systems. And then I will present you our result for Polariton scattering and Polariton interactions. So I would like to start with an experimental fact that I think we all know very well, which is that microcavity Polariton made of two-dimensional excitons are interacting quasi-particles. And this is in fact because of this Polariton-Polariton interactions that this system are interesting. And so typically in experiments, Polariton-Polariton interaction gives rise to optical nonlinearities. And so often there are many Polariton in the place, and Polariton interaction can lead to a variety of phenomena such as optical bistability, superfluidity, or also the blue shift of a Polariton condensate. And here is a state-of-the-art picture of such interaction-induced blue shift, where we see that the chemical potential of the condensate scales linearly with density, at least at reasonable density. Also recently, there has been a signature of Polariton-Polariton nonlinearity at the very few Polariton number level, measured through photon-photon correlation measurement, as we have seen yesterday. And furthermore, as we know, Polariton carry a pseudospin associated with light polarization and the exciton pseudospin, and these define two different interaction constants, alpha 1 for Polariton interacting with the same spin, and alpha 2 for Polariton with opposite spin. And it's known from experiments that these constants are different from zero and that Polariton interact. Okay, this is the experimental point. But here I would like to take a step back and say that actually this is not very clear why two-dimensional Polariton interact. And because scattering theory in 2 dimensions tells us that the interaction should vanish in the low energy limit, or more precisely, this is the two-body scattering amplitude, which vanishes in the low energy limit if the two particles interact via a short-range potential. And this scattering amplitude takes a universal analytical form that I have written here. And I have expressed it in terms of T, which is the T matrix that I will use later for Polaritons. But here is the analytical formula. And the important point is this logarithm here in the denominator, where epsilon b corresponds to an energy scale associated with the two-body scattering length. So for 2D excitons, this energy scale should be of the order of the exciton binding energy. And capital E is the relative kinetic energy. And here we see that when E tends to 0, then the logarithm diverges, and so the scattering amplitude vanishes. And this result is really an effect of the dimensionality, and this is very different in 3D, for which the scattering amplitude is finite at low energy. And this two-body result has, in fact, important consequences when we start to deal with dilute many-body system at low temperature. And for example, for dilute Bose gas at 0 temperature, this implies that the chemical potential should not scale linearly with density, but should have also this logarithmic dependence on the density shown here. And this, again, differ from the 3D case for which the chemical potential scales linearly with density, and this is because the low energy interaction are finite, exist. Okay, and this brings me to this rather provocative, slightly provocative question: why do 2D polariton interact? And to my knowledge, this problem has not been addressed previously. And I guess that we have found an answer, and this answer is quite funny, because in fact, we have understood that polariton are able to interact because they are made of light, or more precisely, because of two important generic features of polariton, the Rabi splitting and the very small photon over exciton mass ratio. So this is the main slide and the main message of my talk. And now I will proceed to try to present you our model and our result in more details. So we start with the exciton-photon model, the standard one. But here we consider a multilayer cavity. So we have n, and we consider that all the layers are identical. So we have n excitonic layers here. So here EC is the kinetic energy of the cavity photon, EX is the kinetic energy of monolayer excitons, and the third term here corresponds to the light matter coupling. And also we include the polarization pseudospin with the sigma index. Yeah. So in fact, in such multilayer system, it is known that the cavity mode does not couple to each layer independently, but rather to a bright superposition of monolayer exciton, which is a symmetric superposition of these excitons. And this Hamiltonian, in fact, can be rewritten by introducing this bright and this dark superposition. And then we end up with a two-couple mode model where we have the cavity photon, which is only coupled to this B operator, to this bright excitonic state. And because of the multi-layer nature of this bright state, the light matter coupling, the Rabi coupling here, is enhanced. And this enhancement scales like the square root of the number of layers. And this enhancement of Rabi coupling in multilayer cavity is of course well known, and this is one of the main reasons why multilayer cavity have been grown in the past in order to increase the light matter coupling. But we see that this gives rise also, in fact, to n-1 dark state, where n is a number of layers. And we can understand in this formalism why these states are dark. If we look at the definition of the operators, we see that the B, which corresponds to the bright superposition of exciton, is a symmetric superposition of exciton, so there is no phase factor here. While for the D operator, we see that there are this phase factor, and so this superposition are out of phase and are not coupled to the cavity mode. And for example, for the case with two layers, the bright state is really symmetric and the dark state is anti-symmetric. And while those dark states are typically neglected in the literature, I want to emphasize that they are not completely unknown. And for example, their existence in multilayer cavity is discussed in this textbook written by Alexei and Guillaume almost 20 years ago, maybe a few months or a few years after the first session of this conference. Okay, then we have this two-couple model which gives rise to the two polariton modes that we know very well, and here is the corresponding spectrum. Maybe I can make two remarks, which are that in a multilayer system we should think of polariton as a superposition of a symmetric superposition of monolayer exciton coupled to the cavity mode, and that in principle in multilayer system there are n-1 dark states which are degenerated and lie at the exciton energy, and those states can in principle exist within the light cone here. Okay, now I will introduce the exciton-exciton interaction, and so in our work we use two approximations. The first one is that we assume that each monolayer the monolayer the layer are not electronically coupled, which means that we assume that excitons are able to interact only within a given layer. And second, we assume that excitons interact via short-range interaction that we model with compact interaction. And this second approximation should be valid when the exciton binding energy is a larger energy scale in the problem. And so this should be particularly accurate for TMD materials because excitons are tightly bound in these materials. Then the interaction Hamiltonian takes this form. So it's just the sum over n for the standard interaction, binary interaction in each monolayer. But then, since we are interested by Polariton scattering, it is useful to rewrite this interaction Hamiltonian in the bright dark state basis that I have introduced previously. And if we do so, this interaction Hamiltonian takes this form. So it has it is very similar to the previous line, but there are a few two differences. The first one is that the bare exciton-exciton coupling here is divided by n. And the second one is that now the four operators on the right here have different indices, and that we have four sum over these indices. Also, there is a Kronecker delta here, which encodes a phase selection, which is associated with the basis transformations that we have performed. But the important thing is that in this basis, this V contains much more term than in the previous basis. And this, in fact, highlights that multilayer systems are quite complex from the point of view of the number of scattering processes which can occur in those systems. And in particular, this V interaction Hamiltonian does not contain only term with this B operator, but contain many other terms. Okay, so then we are interested by Polariton scattering. And in order to calculate this, we use the T-matrix approach, which consists to build a T operator, which is the infinite bond theory in terms of the interaction Hamiltonian V. And so the first term here corresponds to the first order Born approximation, and then we have the second order, third order, etc. But in this approach, we can calculate the matrix element of this T operator, and therefore, which contains all the order of this infinite Born theory. And in multi-layer system, in principle, the higher order term, such as the second order one, can involve dark states as intermediate state for in the Polariton scattering. And here I have illustrated one example of such type of second order processes, which is encoded by the second term, where we can have two polariton which scatter toward two dark states and propagate and then scatter back to two polariton. And this can and so all those terms have to be included and are included in this operator. And then we calculate the elastic scattering between two lower polariton, and it can be calculated, and the matrix element takes this form. And if we further assume that consider the case where the photon over exciton mass ratio is very small, it is very well approximated by this analytical formula that I have highlighted here in red. So here xk is the Hopfield coefficient, mx is the exciton mass, n is the number of layers, and then we have this logarithm where epsilon corresponds to either the exciton binding energy or to the bi-exciton binding energy, depending on the spin channel that we consider. And below, this is in the denominator, this is the lower polariton energy. And here is a very crucial fact. This logarithm here is finite in the low momentum limit because the polariton mode are shifted with respect to the bare exciton one because of the Rabi coupling. And so we can safely take the limit toward k equal to 0 of this formula. And this is how we define the Polariton interaction constant alpha 1, so the triplet interaction, and alpha 2. And here on these two pictures, I have plotted using this formula what we obtain when we use some parameters taken for TMDs, TMD materials. And so on panel A, this is the triplet interaction constant. On panel B, this is the interaction constant ratio. And this is plotted versus detuning. And also here it's for a single layer. So we see that alpha 1 increases when the detuning goes towards positive. And this behavior is dominated by the Hopfield coefficient here in the numerator. And if we look at the interaction ratio, we see that this exhibits some resonances. And those where, in fact, the sign of alpha 2 can change. And these resonances are associated with the parameter point where the collision energy between two lower polariton becomes equal to the bi-exciton binding energy. And this is where these resonances occur. And here I would like to emphasize also that this resonance is not a new phenomenon, and that signature of such type of resonance have been reported a few years ago in single quantum well gallium arsenide cavity. So then we can use our formula to look at the dependency of the interaction strength as a function of the number of layers. And this is what is shown on this slide. So on the first line, this is the triplet interaction. On the second line, this is the interaction constant ratio. And so, and for different detuning, so we can see that alpha 1 decreases with the number of layers, and this behavior is dominated by the n here in the denominator. And this means that while increasing the number of layers increase the radial coupling and increase the light matter coupling, at the same time, it decreases the triplet interaction constant. Well, the behavior of alpha 2 is a bit less trivial because, in fact, the position of the resonance is also dependent on the number of layers. And maybe I can mention that this is actually why in multilayer gallium arsenide cavity, such as 12 quantum well cavity, alpha 2 is negative and very small because we are far away in this right region here of this parameter, even if here this is plotted for TMD parameter. Okay, so just these two slides demonstrate that polaritons interact in contrast to what we should expect for two-dimensional exciton. But one can go a step further and compare the momentum dependence of the Polariton T matrix that we have calculated with the excitonic one, which is given by this low energy formula that I have shown you on the first slide. So on panel A, this is the Polariton T matrix. So the red line corresponds to the exact one, and the dashed black line corresponds to the analytical approximation where we assume the very small photon over exciton mass ratio. And so here we see that the analytical formula fits perfectly well the exact result for relevant momentum accessible in optical experiment. And then if we compare panel A and panel B, we clearly see that the Polariton scattering is larger than the exciton one. Then, so here it's for a single layer, and this is for a triplet scattering. But then we can also see that the behavior of this scattering T matrix is different, the momentum behavior. So in the excitonic case, the T matrix decreases here when we go toward low momentum and eventually reach zero at zero momentum, which is not shown on this logarithmic scale here. While in the Polariton case, we see that there is a maximum, just slightly above the inflection point, and then it decreases because the Hopfield coefficient decreases, and eventually reach finite, saturate at a finite value, and this is how we have defined, I have defined previously alpha 1. Okay, and in fact, two-dimensional polariton.
Yeah, 1 minute. 1 minute.
Okay, I try to go fast. So, in fact, two-dimensional polaritons should also exhibit such type of a logarithmic vanishing behavior, but one can estimate the wave vector at which this logarithmic behavior should occur. And because of this, the photon and exciton mass ratio, this gives a very, very small, incredibly small wave vector, or an incredibly large length scale. And so this is just unobservable in any experiment, and polaritons are interacting and everything is fine. The final step is to compare the polariton T matrix with the excitonic one on larger momentum scale, and this is what is shown here. So the red line corresponds to the polariton case, and the black dashed line corresponds to the exciton one. So we see that at large relative momentum, the polariton T matrix becomes excitonic-like, and one recovers the standard to the result. So this brings me to the conclusion. So we have demonstrated within a low energy scattering approach that polariton interact more than two-dimensional excitons. And I think this result is quite novel conceptually, and in particular, it differs from what we obtain from the Born approximation, because in the Born approximation, exciton-exciton interaction are finite, and then polariton interaction can only be reduced by the Hopfield coefficient here, which is qualitatively different from the results that we obtain. And I think this is why our result is actually interesting. We have obtained analytical expression which should be directly applicable to TMD materials. And finally, we have highlighted that in multi-layer system, the dark states are important for a proper characterization of polariton-polariton scattering beyond the Born approximation. And just before the end, I would like to acknowledge my colleague at Monash University, and in particular, the person involved in this project, namely Guangyao Li, aka Leo, who is another research fellow at Monash University, Jesper Levinson and Mira Parrish. And I would like to advertise you that we have recently found a similar enhancement for polariton electron interaction within a microscopic theory, which is discussed in detail in this two archive paper. And I'm done now. Thank you very much for your attention.
Thanks a lot. Thank you. Thank you. That's very, very interesting. Any questions? I have several questions. So
yes,
first,
Alexei,
on this
please
factor,
cut off your video.
And in the denominator.
Sorry?
Sorry, what?
Could you repeat?
I changed. Can you hear me?
Yes, normally now your video is off,
okay.
And it should be okay.
Yes, sorry for connection problems. So regarding this factor n in the denominator, I was wondering, my intuitive feeling is that the situation must be different if you have just a Boltzmann gas of interacting polaritons and if you have a condensate. So in the Boltzmann gas, we can argue that the probability to find two polaritons in the same quantum well, where they can interact, is going down as 1 over n. But for the condensate, they are correlated. So they visit simultaneously the same wells. So I would expect that this factor n would disappear.
Okay, so first of all, thank you for your comment. So first of all, what we did here is really we solved the two-body problem. So there is no condensate. We try to solve the two-polariton problem within this approximation where we use exciton as structureless bosons. And then, so there is no condensate or no density effect here. But then I don't think that this n here in the denominator is in fact present for condensate as well. And in particular, for example, at least, okay, I can show you the experiment, but in this experiment, which has been carried out at ANU in the group of Elena Ostrovskaya, they measured the Polariton interaction from the condensate blue shift, and they took into account the number of quantum wells. So they had to divide to get a correct result. So this is and this was for a condensate, but in fact this factor n, well, yes, come from this, is inherited from the fact that yes, we have the bright state, from this bright, from the fact that polariton are made from bright state, in some sense.
Okay. Yes, and the other comment concerns electron-exciton interaction that you announced, electron-polariton interaction. It is very important for the story of light-induced superconductivity. So again, there was a for a very long time, there was a question whether things change dramatically if you go from the condensate to the Boltzmann gas of excitons. And I just encourage you to consider this problem within your approach, because it is very important. And I see that also Guillaume wanted to ask something.
Yes, in fact, I did not, there are a few things I did not really understand. Well, I had the feeling that you were saying that there was no exciton-exciton interaction in 2D at k equals 0, whereas in my knowledge, there is no direct dipole-dipole interaction, but there is exchange interaction. Of course, you have to consider the structure of the excitons, and it was computed by Chuti, and it gives in the Born approximation, and it gives the standard result we are always using. So
yeah, so
okay.
yeah. I mean, okay, I know very well that okay, I have not cited Chuti, but I have cited Tassone and Yamamoto, and in this paper, indeed, they calculate. Okay, and in fact, in this paper from Tassone and Yamamoto, they discussed also polariton. So there is this subfield, while I think in Chuti there is not. This is excitons. Well, yes, but okay, this is, in fact, there are many work for exciton-exciton interaction. I think this is a complicated problem on itself, and especially beyond the Born approximation. But I can show you that, in fact, there are people who have calculated this T matrix that we have calculated here for polariton, assuming this contact interaction, but assuming exciton made of electron and hole, and in two dimensions, and this has been calculated in this paper. So this is not TMD. This is another type, but these are for quantum well excitons. And the important thing is that this T matrix and this scattering amplitude, in fact, exhibits this behavior, this logarithmic behavior, as we can see here. And this feature is a characteristic of dimensionality, and this cannot, first, and this is also characteristic of flow energy scattering. And in fact, the Born approximation does not describe very well low energy scattering, and it cannot describe this effect because it's always finite. It can only be finite because in the Born approximation, you calculate maybe with within a microscopic approach with electron and hole, but you calculate this matrix element with this first term. And it is something finite which will give a number anyway.
Yeah, but I understand. We also, in fact, computed in the past this exciton-exciton scattering mediated by B exciton and by dark states. Well, polariton scattering mediated by this, and we had for alpha 2 actually, because
no, but
zero. But so this second order term, but the first order term I am surprised to hear that you say that it is 0, in fact, whereas
No, it is not 0. We do we do not calculate the first or the first and the second. We calculate all the terms, and this is but this is something known. I mean, this is not for excitons maybe too much, but this is something known in two-dimensional scattering theory, low energy scattering theory, and this result here, which say that the scattering amplitude should vanish at low energy is something known. I mean, it is something known in atom, in the atomic community, for example, where people consider atomic interaction, and for example, but yeah, I don't know if I'm clear, but what I want, I can mention, this is because here we use a different approach. This is really elastic scattering, but this includes all the terms, and this is why it is different. And you cannot get this logarithmic, this kind of low energy scattering amplitude with only the first and the second order term in the scattering. And
okay,
also,
I'm afraid we're running out of time already. So I agree with Guillaume that exchange contribution should not be 0 at k equal to 0, and maybe you just neglected. That's why you have this result.
No, we don't have exchange because we consider exciton as structureless bosons. So
yeah, that's fine. That's fine. So there is no any controversy between you two. It's we are both right. Within this approximation, if it is a structureless boson, the interaction goes to 0. So, ladies and gentlemen, I think we should thank all the speakers of this session. That was very interesting.